Okay, welcome back. It's time for the last problem in this chapter. This is a fun problem. It's about KCL, KVL, Ohm's law, and power balance, and also the idea that sometimes things that look like sources can actually be loads. That's going to be in here. And also some tricks on just keeping everything organized. So let's do it. So we've got one of these guys, which is typically a source but could be a load. Okay, so this is 7.2 volts. Then we've got a resistor and then another one of these guys with this polarity on it, and this is 0.7 volts. This guy's 55 kilo ohms. Okay, and then it comes over to this node right here, and it comes on down to this 200 ohm resistor right here. 200 ohms. Then okay, then there's a dependent source, which we haven't seen yet. All right, so this is dependent source, and it has a voltage across it called Vy with this polarity. So it could be a source, could be a load, but it's a dependent device. Dependent. Given by 49 I beta. So I beta is the current that's this guy right here is putting out. This device is putting out I sub beta. Okay, and then this is a dependent device. It's monitoring I sub beta and then putting out 49 times I sub beta. It's kind of acting like an amplifier. So whatever I sub beta is, however many amps this guy is, this guy will put out 49 times that. Okay, so there's some wires that are not shown, by the way. I mean, over here there's probably like a donut transformer, you know, a current sensing device of some kind, and then there's some wires heading over here to send this I beta measurement over to this guy. But anyway, there's 500 ohms here. And there's another device here, which could be a source, could be a load, who knows? We'll find out. All right, so we got all this stuff right here. So this is given, this circuit is given, and we're asked to find V sub y. What is V sub y? And then do a power balance. Okay, so there's a lot of complexity or a lot of potential to get confused here, because some of these devices are going to be loads and some are going to be sources. Now you don't know right now, but I'm going to tell you. This one's a source, this one's a source, and these two are loads. But you don't know that right now. Okay, but that's what's going to happen. And we need to do a power balance. We need to calculate the power out of all of these guys. So this is going to be delivering power, and this is going to be delivering power. Once again, you don't know that right now, but that's what's going to happen. And this is going to be a load, and it's going to be a load. Okay, these three resistors right here, they're going to be loads, because resistors are always loads. But the point I'm making is there's a lot of stuff to keep tracking here. So that's part of what this problem is about, is just keeping track of all the information. So, and the other thing is we have all these power formulas, but because of the confusing nature of this problem, it's better if we just use this one. Just use P equals IV. So if we solve for all the voltages and all the currents in all these devices, we can just use this guy and make a nice organized table. Okay, so let's get started. We don't know what I beta is. We know that this is 49 I beta. So right away we know what this is. We don't know the quantity, but we can express it in terms of these other two, right? We've got I beta coming out of this thing. Well, it's coming in, but it's also coming out, right? It's going through this, around this branch. So I beta is coming into this node A, and 49 beta is coming into this node A. So this must be 50 I beta, right? So this is 50 I beta. So we can get that with KCL at A. I mean, I just figured it out by looking and stuff, but you know, formally, and we do need these formal ways for when it's not so clear. So you know, in equals out. So 49 I beta plus I beta equals 50 I beta. So that's what's coming out. So this is 50 I beta. Okay? So we don't know what I beta is yet, but we know that this is this current in this branch here is 50 I beta. So what do you want to do next? Well, it's not obvious, but we've got a couple of KVLs we could do. We've got one loop in here we could do, and we've got another loop in here we could do, and then we've got a loop around the outside. We could just choose one, but let's look at this loop right here. If we do this loop, well, we have 9 volts given. We have 50 I beta volts given here. We have 49 I beta here. There's going to be 2 unknowns in there. There's going to be I beta and Vy. So let's not do that right now. Let's look at this guy right here. What do we got here? We've got 7.2 volts. We've got a voltage here that's known. Voltage here known, voltage here known. We've got a voltage here that would be 55K times I beta by Ohm's law. So I beta would be the unknown. And then here we've got a voltage that would be 200 times 50 I beta by Ohm's law. The only unknown would be I beta. This loop should give us I beta. If you're not sure, you can just start writing KVLs and writing KCLs, and then just look at the algebra and try and get an algebraic solution. You can do that. Honestly, do them like I'm doing them, because there's some lessons in that. But once again, when we get to chapter 4, we're going to find a better methodology to do these guys. All right, so look, I'm going to do this loop right here. Call that loop 1, because that's going to give me I beta. So we'll do KVL at KVL loop 1. All right, so we're going around here, and we're coming. Let's see. We're coming. Let's start at this, just to have a positive term. We're coming into this positive terminal, so we're going to have 0.7 is positive. Okay, then this voltage drop. We need to put the arrows, the voltage polarities on here. So if I beta is going around this way, this is the polarity, and if 50 I beta is going down this way, then this is the polarity. Okay, so this thing here by Ohm's law, this voltage right here is 55,000 I beta, and it's positive because I'm coming into the positive terminal. Okay, this dude right here by Ohm's law is 200 times 50 I beta by Ohm's law. Right here we're doing Ri, and then Ri. The I through here is 50 I beta, and the R is 200. So this is R. This is I. Right here, this is R. This is I. Okay, and we're coming into the positive terminal, so this term is positive. We're coming into the positive terminal. This term is positive. We're coming into the positive terminal. This term is positive. Here we're coming into the negative terminal, so this term is negative 7.2 volts. Those sum to 0. Okay, the only unknown here is I beta. So solving for that, I beta is going to be collecting the 7.2 and the 0.7 on the other side, and factoring out the 55,000, and then 200 times 500 is 10,000. Factoring that out and moving these guys to the other side. So I'm doing several algebraic steps in one there. If that's confusing to you, then do the steps individually. So generally speaking, try and keep a clear head. If you need to go slower and show more steps, then absolutely do so on your own. I'm trying not to clutter the stuff up with too much detail. I'm trying to keep a certain level of abstraction, but there's nothing wrong with showing all the detail in your homework if you need to. Anyway, this works out to 100 microamps. So we got an answer now. We got a value, so that's why we did that. Now back to this loop over here. That one's going. that one's going to have Vy and I beta in it, as we talked about previously. So let's go ahead and write this guy. So KVL, let's call it 2. Let's go. So which way to go? Well, I like this is, I like to think of the power coming, or the current coming out of the positive terminal. So if you did that, it'd be going around this way in the loop. Just that's what I did over here. I thought of the power, or the current rather, coming out of the positive terminal. You know, I just chose these guys to focus on. You know, if you choose something different, you'll end up with negative signs floating around. You know, which is fine. You can correct for that. But anyway, so let's write the KVL2 here. So I've got going around this way. I mean, coming into the positive terminal on this, and I'm summing voltages. So I can use Vy, because that's the voltage across this device. Right, so I'm coming into the positive terminal on this device, so it's positive Vy. I'm coming into the negative terminal on this device, so it's minus 9 volts. Okay, I didn't put the polarity on this guy here, but if the current's going around this way, then the polarity would be this way. So that's going to be positive 500 times 49 I beta. Once again, this is a R I term. So this is a voltage together here, and I'm summing voltages. And then this dude here going around this loop, this guy, it's going to be coming in the positive terminal, so it's positive 200 times 50 I beta. Once again, this is R I. Is that all four? 1, 2, 3, 4. There's 1, 2, 3, 4 devices. Those sum to 0. I know I beta. It's 100 microamps. So the only unknown here is Vy. So I can solve for Vy. So Vy is going to be, it's going to be 9 minus 500 times 49 times 100 micro, which is 0.0001 minus 200 times 50 times 0.0001. Okay, so it's going to be 5.55 volts is the answer. So that's one of our answers. Okay, so now it's time for the power balance. So this is where it gets tricky. I guess we could review this a little bit before we go on. Not really. Just look at it again if you need to. So it would be nice to just use P equals IV on all of these dudes. And some of them are loads and some of them are sources. And it's not necessarily clear yet what's going on. So let's make a table. So there's element, and let's put the current, and let's put the voltage, and let's do the power, and then anything else that happens. So we've got this guy. We've got this guy right here, the 7.2 guy, which has 7.2 volts in him. So this is voltage in volts. Okay, then we've got this 55 kilo ohm resistor. There's a 55 kilo ohm. And then we've got this guy. We've got the 0.7 volt device, which has 0.7 volts in him. Draw a line here. That's the three elements on this side of the branch. Then I've got this guy in the middle. I've got the 200 ohm guy, and I've got then I've got these three guys over here. So I've got this guy, and the voltage in that guy was 5.5. We just solve for that. Okay, then I've got this 500 ohm resistor, and then I've got this this doohickey here, this 9-volt thing, which has 9 volts in it. Okay. These three guys, these guys right here, they all have I beta in them, which is 100 units or microamps. So this has 100, this has 100, this has 100. This dude right here, it's got 50 times that, so it's got 5,000 microamps. This guy. And these three guys all have 49 I beta in them, right? That's what this guy's putting out, and in order to make a valid connection, they all have to have that same. They all have to have that same current in there. So these three dudes have 4,900 microamps. All right, and so I have these V and I could calculate the power right now. It's going to be 720. This is going to be 70. This is in microwatts. This guy, because I have VI. This is going to be 27,195 microwatts, and this guy here is going to be 44,100 microwatts. Just 9 times 4,900 and 5 times. Okay, if I had the voltage in these guys, I could get the power in there, and I can get the voltage by Ohm's law here. So by IR, this is going to be the voltage. 55,000 times 100 micro is 550 volts. Seems like a lot. That's not right. It is too much. It's 5.5. That's more reasonable. 5.55. This times this. Write that out bigger if you need to, with the times 10 to the minus 6, or with all the zeros and stuff. Okay? Or enter it into your calculator carefully with the micro and the kilo. Anyway, then IV, these two guys down here, 100 micro times 5.5 gives you the power. That gives you 550. Likewise, this guy here, using IR, I can get it's going to be 5,000 micro times 200 gives you 1. And this guy here is also IR. So by IR I can get 4,900 micro times 500 is going to give me 2.45 volts. Okay, then I can do the power here. I can do 1. Yeah, 1 times 5,000 is 5,000. Last time I checked, and then 4,900 times 2.45 gives you 12,005. All right. Who's a load? Who's a source? So you need to look at the polarities on these things. So load or source. Well, let's do the current going this way for all of these dudes. So the current going this thing, it's minus to plus. That's a source. This is a source because this I beta is coming out at the positive terminal. It's coming in negative, out positive. That means it's basically, it means it's coming out with more potential. It's a load, and that's what's happening over here as well. 49 I beta is coming out of the positive terminal, so it's minus to plus. This is a source. Okay, the resistors, they're resistors. That's a resistor. This is a resistor. This is a resistor. So they're all loads. What about these other two guys? This round guy, the current is coming into the positive terminal and out the negative. It's coming in the positive and out the negative. That's a load. This round guy's a load. This dude, the 49I beta arrow here, is coming in the positive and out the negative. It's coming in the positive and out the negative. That's also a load. Okay? So these two dudes are loads. And these two are sources. Okay, so if you add up this and this, you're going to get 44,820 absorbed. No, well, supplied, but these three here, you're going to get the same thing. So 44,820. This is, these are load and this is source. Okay, so these two elements are in total putting out 44,820, and then everything else together is using up 44,820. So they balance, which they should. Once again, if they don't balance, you either invented a new power source and you're going to be fabulously rich, or you made a mistake. And it's probably the latter, but I tell you, if it's the former, if you invent a power source that's revolutionary and you end up with more source than load, then don't forget about me. Like when you're a billionaire, money just don't know what to do with. Remember poor little Professor Ross. And maybe you could buy me a car or something. All right, get these done. We'll learn better ways to do these things. That's the point of the course. All right, follow this methodology as much as you can. Do the problems like I'm doing them, except that write them up neater. All right, bye-bye.